Hello, welcome to this video. In this video, we will start solving numericals on vapor compression refrigeration cycle. Let us read the problem. In a saturated vapor compression refrigeration cycle, so he is saying that it is a saturated vapor refrigeration cycle, which means at the entry of compressor, it is assumed that the refrigerant is in saturated vapor condition, alright. Operating between evaporator temperature minus 10 degrees Celsius. So, evaporator is at minus 10 degree Celsius, and condenser temperature is at 40 degrees Celsius. Okay. The enthalpy of refrigerant freon. So, freon 12 is the refrigerant. So, freon 12. If you have to see the table for properties of enthalpies, I will have to go to freon 12. At the end of compression, so enthalpy of refrigerant at the end of compression. So, after compression, the enthalpy will be, after compression, enthalpy is 220 kilojoule per kg. Now, he is asking us to show the cycle on TS diagram, okay, and pH planes. So, let us draw these two planes now. So, we will have TS and pH plane, okay. So, one is temperature versus entropy and the other one is pH. We know that both of them will start with vapor dome. pH chart, it will be like this, and TS chart, it will be more like this. Anyhow, so we will start from point 1, that is dry saturated vapor, because it is saturated vapor compression. So, point 1 is the entry to the compressor, at least we want it to be here, and he has also given it is a saturated vapor. And we know that it is a reversible adiabatic or isentropic compression. So, isentropic compression would look like a vertical line in a TS diagram, because S is equal to constant, okay. Because S is equal to constant, it looks like a vertical line. Then this will be outside vapor dome, it will be constant pressure, looks like this in a TS diagram. And inside vapor dome, temperature and pressure both will be constant. So, it looks like this horizontal line within vapor dome. So, 2 to 3. Then remember 3 to 4 is a throttling, which is isenthalpic process where enthalpy remains constant. Alright, this is pressure constant by the way, 2 to 3, this is entropy constant. Then 3 to 4 looks like a curve, H is equal to constant in a TS diagram, and then your back constant pressure heat rejection or constant temperature heat rejection within vapor dome, that is our evaporator 4 to 1. Okay, this is our TS diagram. Let us go to pH chart. Now, in a pH chart, constant entropy looks like, here I am starting from again saturated vapor, that is 0.1, it has to be on this line, 0.1 has to be on this line, alright. So, 2 to 3 is a constant pressure heat rejection in condenser. So, it looks like a horizontal line in a pH chart, because pressure and temperature both are constant, alright. So, 1 to 2 is entropy constant, this is how it looks like in a pH chart. In 2 to 3 is constant pressure heat rejection. So, pressure constant looks like a horizontal line, and then throttling is a isenthalpic process where enthalpy remains constant, alright. So, enthalpy remains constant. So, it has to be like this horizontal vertical line. Then this is 4, then 4 to 1 is constant pressure. So, this will be like this. So, this is again pressure constant, this is enthalpy constant, okay. Now, let us go for the question. We have drawn cycle on TS and pH planes. Just because he has told that saturated vapor compression has started the point 1 from here, it may be deviated little bit there, or it could be within vapor dome, that will alter accordingly. Now calculate COP. The first sub question is calculate COP. Second one is refrigerating capacity, that is how much heat we are removing, QL or heat removed, you can call it as, that itself is refrigeration capacity. And the third one is compressor power, that is work. And remember, refrigerant flow rate is given. So remember, mass flow rate is 1 kg per minute. Okay. Now let us go back here. The refrigerant is Freon 12 operating between -10. So the temperature here which we are talking, this is -10 degrees Celsius, and it is operating at condenser temperature of +40 degrees Celsius. Alright. So -10 and +40 degrees Celsius. Freon 12. The enthalpy of refrigerant at the end of compressor is 220 kilojoule per kg. At the end of compressor means he is talking about the H2. So I will rename it as H2 is equal to 220 kilojoule per kg. Now how shall we find out enthalpies? Because we know COP can be found out by having enthalpies at all state points. So it is important that we will find enthalpies at each point, then it is going to be easy for us to calculate any of these questions. I will start with H1. So H1 is on the vapor dome and it is on right side of the vapor dome. So it is a saturated vapor. So H1 will be equal to Hg at what temperature? -10 degrees Celsius. From data handbook, of course, from data handbook, we can see for Freon 12 data handbook, I mean Freon 12 table, Hg at -10 degrees Celsius, if you see, that will be the value of H1. H2 himself he has given 220 kilojoule per kg. Now let us go for H3 is equal to H4, because H3 is equal to H4, enthalpy constant. Now H3 is equal to what? H3 is equal to HF, because if it is a saturated liquid, it is denoted as HF in our data handbook. At what temperature? At 40 degrees Celsius. Now let us go to the table Freon 12. I have copied it here. So Freon 12 table. Okay, in our BT Nijaguna data handbook, the table is B3. So Freon 12 data handbook table. At -10 degrees Celsius, at -10 degrees Celsius, I want Hg. So it is tabulated here, Vf, Vfg, Vg, Hf, Hfg and so on. So I will have to go for -10 degrees Celsius row and I want Hg. So Hg is 183.058. 183.08 kilojoule per kg. Now what is H3? HF at 40 degrees Celsius. I will go to 40 degrees Celsius HF. So I will go to 40 degrees Celsius. Now HF is which column? HF is 6. Column number 6. Column number 6. That is 74.527. All right. 74.527. Now we have enthalpies at all salient points, right? H1 is there, H2 is here, he has given, H3 and H4 is known to us. I think now we are ready to go for COP. Let me go for COP. Now COP is equal to desired output by input. Now desired in a refrigeration is heat to be removed divided by the work which we are supplying. Now heat to be removed is from here. So this is what is Q to be removed and this is what is the work we are supplying to the compressor, and you can show that same in pH chart as well. Heat to be removed and this is a W compressor. All right. So heat to be removed can be written as H1 minus H4. The W can be written as H2 minus H1. Now substitute back here. H1 is 183.058 minus H4 is 74.527 divided by H2 is 220 minus H1 again 183.058, and we know the range of COP has to be between like 1 to 6. Let us calculate this. 183.058 minus 74.527 divided by 220 minus 183.058. That will be 2.93. So, COP of this plant is 2.93. Now, let us go to the second part. The second part is calculate refrigerating capacity. Now, refrigeration capacity is simply heat is removed, right? Refrigeration capacity is heat removed, all right. Now, heat removed is of course H1 minus H4, but the moment he asks you in capacity, you can also keep it in kilowatt because mass flow rate is given. Now, what is 1 kg per minute? This please convert it 1 by 60 kg per second. All right, I will substitute that mass flow rate here. So, before that you can also keep it in kilojoule per kg as well. For example, H1 is 183.058 minus 74.527. All right. Now, that will give us in kilojoule per kg. 183.058 minus 74.527. So, 108.531 kilojoule per kg. Kilojoule per kg. But if you want it in kilowatt, multiply this by kg per second, because kg per second multiplied by kilojoule per kg will give us kilowatt. Kilojoule per second is kilowatt. Okay. So, m dot into H1 minus H4. Now, that means I will go for 1 by 60 multiplied by 108.531. So, that will give me refrigeration capacity. So, 1 by 60 into 108.531, 1.80 kilowatt, 1.80 kilowatt. Now, let us go to the sub question 3 work. Okay. Sub question 3 is work applied to the compressor. I mean power. All right. The moment he asks you power, it is better you multiply this m dot with m dot. So, what is the equation for power? That is H2 minus H1, compressor work. All right. So, 1 by 60 into H2 minus H1 is 220 minus 183.058. So, that will give me the power or compressor work in kilowatt. 1 by 60 into 220 minus 183.058. So, 0.6157 kilowatt. Okay. We shall start solving few more numericals in the next class. Thank you.